Welcome back. Let's talk about Gibbs free energy. If our goal is to predict whether a reaction is going to be thermodynamically favorable, thermodynamically unfavorable, or is at equilibrium, we have two choices. The first is to use the second law of thermodynamics. The second law of thermodynamics says that for a thermodynamically favorable, also known as spontaneous, process, the change in entropy for the universe will be positive. Delta S for the universe, that's the change in entropy of your system you're studying and everything else around it. So for a thermodynamically favorable process, delta S will be greater than 0. If delta S is equal to 0, you are at equilibrium. The downside to this method, although it is always true, is that it's really hard to measure the entropy change of the universe. The universe is just a really big place, and so while we might be able to measure our system, getting all of the surroundings and everything else around it is very challenging. We need a better way. That's where Gibbs free energy comes in. Gibbs free energy is a way to assess whether a chemical process will be thermodynamically favorable, unfavorable, or at equilibrium, allowing us only to focus on the system. And so if Gibbs free energy, which has the symbol capital G, if the change in Gibbs free energy is less than 0, then our process is going to be favorable in the forward direction, or as we have it written. If delta G is equal to 0, you're at equilibrium. And if delta G is positive, it's greater than 0, then the reaction is not thermodynamically favorable as written. The reverse reaction, however, would be. So what is Gibbs free energy? Gibbs free energy is a new state function, just like enthalpy and entropy, and it is defined as the enthalpy minus Ts. So T here is our temperature in Kelvin, H is the enthalpy, and S is our entropy. More often than not, what we want to know is how our Gibbs energy is going to change over the course of a process. So typically we're measuring delta G. And so this equation has a very, very close analogy, which is delta G is equal to delta H minus T delta S. And here we're assuming that this process is isothermal, so it's being carried out at a single constant temperature. And if it happens to also be under standard conditions, then we have delta G naught equals delta H naught minus T delta S naught, where that naught above each of our characters is indicating that we do indeed have standard conditions. So what Gibbs energy is telling us, this value for delta G, is it's really giving us a measure of the stability of the system. And so the lower your Gibbs energy is, the more stable the system. So the system will naturally go to find the lowest possible energy. If we look at a reaction coordinate diagram, I've got two drawn below, where on the x-axis is the reaction progress. So reactants will be on your left and products will be on your right. You have free energy on the y-axis. You'll see that the reactants and products have different free energies. In this case, the reactants have a higher free energy, they're less stable, and the products have a lower free energy. This reaction is going to continue until it reaches the lowest possible energy for the system, which would be right about here. And that's where that reaction is going to stop. There is no longer a driving force to move forward any farther. If you had started with all products, you would have made some reactants, again, until you reach that minimum in free energy. At that point, there is no longer a driving force for the reaction to continue. That is where equilibrium occurs. And to connect Gibbs free energy to our equilibrium conversation from before, if you look at this particular drawing, the equilibrium is found when you have slightly more products than you have reactants. Your equilibrium constant will be greater than 1. On the contrary, my other picture is a similar diagram. Here again, we're looking at Gibbs energy as reactants turn into products. And in this case, the minimum favors the reactants. You'll have more reactants, less products. Thus, your value for K is going to be less than 1. You will have more of the reactants. When it comes to calculating a value for delta G, you can do so directly using the equation delta G equals delta H minus T delta S, and this can be under standard conditions or not. You simply need to plug in the values. If you know a value for delta H and you know a value for delta S, you plug them in. Note a couple of things. Temperatures must be in Kelvin, and make sure your units match. Delta H's are typically given in kilojoules per mole, where entropy values are more often tabulated in joules per mole Kelvin. So you're going to have to convert one or the other so that you'll have consistent units throughout your problem. And so for this particular process, once I converted everything, plugged it in, did the math, I got a negative 143 kilojoules. And so, per mole. And so since delta G is negative, this is a favorable process. We can also calculate delta G naught indirectly. So for many materials, Gibbs free energies of formation have been tabulated. And just as we did for enthalpy, to find the Gibbs free energy for a reaction and how that changes for a reaction, so delta G naught, you can sum the Gibbs free energy of formation of the products minus the sum of the reactants. Make sure you take into account any coefficients in the equation, but other than that, it's just like you would have done for enthalpy. Lastly, I want to talk about how Gibbs free energy is impacted by temperature. If you think about trying to have a process being spontaneous, since delta G is delta H minus T delta S, and because delta G is negative when you have a spontaneous process, a value for delta H that is negative tends to favor spontaneity because it tends to lead to a negative delta G. In contrast, a value for delta S that is positive, an increase in entropy, tends to lead to a value of delta G being negative mathematically. This makes sense. Lower energy tends to be more stable, so that's going to tend to lower your Gibbs free energy. More entropy, more available microstates, more probable, that's going to tend to cause a reaction to be spontaneous. So those two factors go into play to determining whether delta G overall will be positive or negative. As a result, if you take a look at Gibbs free energy, if delta H is negative and delta S is positive, regardless of the temperature, you're going to get a negative sign for delta G. So if you've got an exothermic process with increasing entropy, it'll always be favorable regardless of the temperature. On the contrary, if delta H is positive, so an endothermic process, and delta S is negative, you're decreasing entropy, those are going to lead to a process that regardless of the temperature will not be thermodynamically favorable. The interesting cases is where you have a mix. If both delta H and delta S are negative, delta H is favoring spontaneity, but delta S is not, then it depends on the temperature which one dominates. At low temperatures, and low depends on the reaction, at low temperatures, your value for delta H is more important because the T delta S term will be small. So at low temperatures, delta H dominates. At higher temperatures, that T delta S term can get very large, and the impact and importance of the entropy comes into play. And so it depends on what the signs are. If both are negative, at low temperatures, since delta H is dominant, you're going to get a value for delta G that's negative. It'll be spontaneous. At high temperatures, it will not, because your entropy, which was not favoring spontaneity or not thermodynamically favorable, will dominate. The opposite is true if they're both positive. At low temperatures, delta H being positive will make the reaction be thermodynamically non-favorable, whereas at higher temperatures, entropy dominates and the reaction will be favorable. When it comes to this type of problem, stop, be methodical, use logic, and think about what's going to be the driving force at a particular temperature. So in sum, Gibbs free energy gives us a really nice snapshot by looking just at our system to decide whether a chemical process will be thermodynamically favorable, delta G is negative. Thermodynamically unfavorable, delta G is positive, or if it is at equilibrium when delta G is 0 and there's no driving force in either direction for the reaction. You can calculate delta G both directly and indirectly, and temperature can have an impact on the sign for delta G depending on the relative signs of delta H and delta S.